Welcome you all to this course on defects in material. Okay. Today we will have the class on defect interaction. Okay. So far we have considered today's class is on defect interaction. What are the defects which we have considered? Essentially point defects, dislocations, stacking faults, then defects in ordered lattices like antiphase boundaries and domain boundaries. Okay. And then we have considered interfaces. Okay. And this defect interaction controls the quite a bit of almost all the properties of this material. Okay. Electrical property, optical property, magnetic property, mechanical property, all these properties are controlled by defect interaction. But what we will do is that since this course is essentially on mechanical side of it, it's mainly for metallurgists, we will concentrate mainly on the defect interaction on mechanical properties. Okay. Essentially we will consider some of these interactions. One, so we know that the deformation of the material is essentially controlled by moment of dislocations, and this dislocation can interact with these various types of defects which are present. So essentially what we will be looking at in today's class is dislocation defects interaction. Okay. Okay. When we talk about this, what are the defects which we have considered? One, vacancies, self-interstitials, okay, substitutional, in interstitials, impurities in both in substitutional and interstitial sites. These are all the ones which we'll consider. Okay. All these point defects when we consider, okay, we have earlier looked at the various types of point defects in ordered as well as disordered lattices. Okay. How to identify the various point defects. Okay. Their concentration. All these aspects we have looked at it. But what does point defect do? Like a vacancy, if it is present or an interstitial is there, it is going to distort the lattice. Okay. Either it could be a contraction or it could be an expansion which can happen. Okay. The same thing will happen with either substitutional or interstitial impurities also which are added. Okay. Then they will generate, when they distort the lattice, essentially it is generating a strain in the lattice, correct? Okay. So they generate a strain, and how this strain, okay, is going to interact with the stress field due to the dislocation. Okay. That is, this will give us, if we take the stress multiplied by the strain, that will give what is the energy change which is going to take place in the lattice. That's the information which is necessary. That will tell you whether that is a repulsive type of whether it's an increase in energy or decrease in energy. Depending upon that, we can decide whether it's attractive or repulsive type of an interaction which is taking place. Okay, that is what essentially is required. Okay. Suppose we assume that the simplest way a vacancy or a defect is there. Assume that some area of that sample is there, into which we are putting a defect. Maybe the radius of it is, you assume it to be RA, Into this region, we are introducing a defect which has a RA into 1 plus delta, I will write it. Delta is the misfit parameter. That means that it has a, which is slightly larger lattice parameter. So this is the misfit. If I introduce this into this area, okay, there is going to be a change in volume which we can find out how much it is going to be, the misfit volume change. But once it has been introduced into the lattice has got its own elastic constants associated with it. So what is essentially is going to happen is that some part of the strain will be accommodated in the matrix, some into this vacant side. So it reaches a size that is with the misfit. If I take it, if this is that size, RA plus delta, it comes. What it will reach is that finally a size which will be somewhere in between, so that that means that the strain which is introduced into the lattice is not the same as the misfit, correct? This one can find out, and it is essentially given by this relationship that epsilon will be equal to into delta. Okay, this relationship from elasticity theory, linear elasticity theory, we can derive it. I am only just giving this expression. Okay, essentially what it is that strain and the misfit are related. Okay, we mentioned that we can find out the product of strain and the stress field of the dislocation value. This defect we are considering it as a volume defect. Okay, we can find out what is the volume change and what is the volume strain. Okay, that volume strain is nothing but some delta V divided by some volume will be there, plus the stress could be essentially around the whole volume. If you take it, it can be taken to be, the stress P can be taken to be 1 by 3 into Z, correct? That if you take that, then the energy will be P into delta V, we can write it. This is also an energy term. Okay, so this energy is the interaction energy. Okay, if you do a substitution and find out what is the net change, okay, this will turn out to be, some terms will be there. Okay, a constant I will put it, sin theta will come. Okay, what essentially it is going to happen is that this constant will consist of shear modulus, okay, then the volume term, some part 4 pi RA squared will come, and the strain also will come into the picture. Okay, what is essentially important if you look at it is that the interaction energy or the change in energy which is taking place is inversely proportional to R. Okay, depending upon the sign of that epsilon, the strain will depend upon whether it's a contraction or an expansion. That will also decide whether it's positive or negative, correct? Immediately one can understand that suppose it is a vacancy which is going to be there, then there is going to be a small contraction, so interaction energy is negative. That means that whenever we consider an edge dislocation, this vacancy, if it comes, that interaction, it will be on the side where compressive stresses are going to be there. Okay, if it comes there, it will relieve, and if it is going to be on the other side, it will be the interstitial atoms which will be coming there. Okay, the sign of interactions will change depending upon that. Not only that, okay, this interaction energy also tells that there's a sort of a binding which takes place between the defect. This one, if the energy is negative, then what's going to be, it is getting attracted towards the dislocation. Okay. The consequence of here we had calculated the energy, but the other aspect of this interaction of vacancy with a dislocation we have already considered earlier. Okay, where what is going to happen is that when a vacancy interacts with a dislocation, it introduces a jog into the material, right? When a dislocation is there, it comes and gets attached, it will be shifting in locally, a jog will be created in this the region where it has come. Okay, this jog, what it is going to happen, okay, and then we looked at how this dislocation will move. We have seen that the jog is essentially is not in the slip plane. Because of it, it's not able to move as fast as the dislocation, so it has to be dragged. That itself gives rise to hardening of the material. That's one consequence of it. Here we are looking at the other part of it. When they are even further away, there is an interaction. The maximum, when that come as close and joins with it, then that's the maximum energy gain, right? If you look at what is going to be this interaction energy, essentially this value I think is about 3 times that delta, okay, which turns out to be into EV for metals, most of the metals. And in the case of like semiconductors, it is some 20 times delta electron volt. This is what the energy of it is, which has been some values, okay, which calculations have shown. Okay. Here what we have considered is only one aspect of the interaction energy. Okay. There's another aspect also which we can, there are many aspects which we can consider. So, suppose we assume that the point defect is there. What will be the modulus of the point defect? It's almost 0. What's the modulus of the dislocation? It's going to be high. That of the matrix, modulus of the matrix is there. When they interact, there's going to be a modulus effect where when it reaches dislocation, that region segment, if it is lying there, it has a modulus which is small. This is going to be there in even in a material where a second phase particle is there. That is, if a dislocation moves in a material, okay, we know that the self energy of the material, okay, is given by this formula, roughly half GB squared. Correct? Suppose the modulus of the matrix is Gn, which is greater than that of the modulus of the precipitate. Then the segment of the dislocation which is going to be in the or in the vacancy, if it is going to be, I'll put it, equals half into, that is this modulus, this self energy is small compared to that of the one in the matrix. So when it enters, we require higher stress to be applied to take the dislocation out from that. That means that that also shows that there is an interaction, correct? This interaction is also an attractive one. Suppose we assume that, consider the case when the second phase, this region which we are considering, it is that sample, this region has got a modulus which is much higher. Then the self energy of the dislocation within that region is going to be very high. So it would always try to prefer to be away from it. So there's a sort of a repulsive force which will be acting when they come close by. Correct? So here what is going to happen is that as the dislocation tries to enter here, there will be a repulsive force, it will try to keep away, whereas in the other case it is attracted towards it. So the interaction energies are. So modulus also gives one more interaction. So all the interaction energies will be acting at different length scales, at different positions. That is, suppose this is where we have the defect which is present. Depending upon this distance, okay, the interaction energy will change. Okay, that is what essentially is going to be only this. This interaction energy is essentially the stress and strain field interaction which is going to give rise to. The other one is that the modulus effect will come into the picture only when it just enters, because it's not going to act, correct? Then, and another effect which can happen is that, which normally is ignored, is that whenever we look at an edge dislocation, okay, in the edge dislocation, there is a compressive stress here, okay, this is compressive, and tensile is going to be there. So closer towards this core, if you look at it, in this region, there's going to be less of atoms, means that atom is not going to be there. That region has to be replaced with some electrons which have to come, correct? And here it will be the other way around. Positive, this one will be there. That means some dipole interaction will take place. These dipoles can also interact with, whenever defect is being present, there also, if you look at it, there's going to be a variation in the electron density, correct? So that interaction also will take place. Okay. In cases like ionic materials and all, where these interactions may be stronger, in most of the metallic cases we just ignore them. Okay. Then there is another type of an interaction which can happen, is that in many materials the dislocation can split into partials. Whenever the dislocation splits into a partial, the region between them, we call that a stacking fault is created. The stacking fault is nothing but a different phase, correct? It's a nuclei of a different phase. When a nuclei of a different phase is there, the compositional effects, how much the defect can be dissolved in it, is going to be different. Not only that, for that phase, since the chemical composition also can be different, the chemical potential between the faulted region and the unfaulted region will also be different, right? This chemical potential, what will be the effect of this change in chemical potential? More solutes can come into the stacking faults and segregate to them. So that's another way in which they are attracted to it. Okay, this effect is called as the Suzuki effect. This is another type of effect with which solute segregation will occur. So these are all the various types of interactions which point defects can have with dislocations. Is it clear? Okay. This sort of interaction, what is the consequence of it? Here we have considered vacancies. Now let us take the case of a substitutional or an interstitial solutes also, which we can consider it. Okay. Suppose the defect is present, a substitutional defect is present, okay, or an interstitial defect is also present. This defect can have a positive misfit or a negative misfit. Okay. This change in misfit will make the defect segregate preferentially to the above the slip plane or below the slip plane in the case of an edge dislocation. Because if the misfit is negative, that is, then what will it will segregate to the compressive region, correct? If the misfit is large, positive, it will segregate to the tensile portion of the dislocation. This gives a bias also. And more than that, what we have considered so far is essentially a defect which is isotropic. Quite often defect could be anisotropic also, like in iron. when carbon goes to an interstitial position, it occupies a position which is an anisotropic, where the defect essentially is, the defect has a side symmetry which is essentially tetragonal. That means that in some directions, if you look at it, the misfit will be small when the carbon atom sits onto the cage. In another direction, that is along the c-axis, it's going to be a large. The strain will be large in those directions. So finally, it doesn't matter whatever is that. When we have to find out the total interaction energy, we have to take the misfits in each of the direction into account and then calculate the total energy. Okay. It is. But this interaction energy, what it brings out is the fact that there will be a preference for defects if they come close to the core of the dislocation. Okay, there is an energy minimization is going to be taking place. That means that suppose we consider an alloy which contains small concentration of defects, which could be either interstitials or vacancies. Interstitials or substitutional impurities are present there, very small concentration. What we mean by small concentration essentially is that the defect that between the interstitial interaction is very small. Okay, they are so isolated that there is no interaction between them. That's the way we look at it. Okay, these defects, generally we assume that the concentration is uniform, correct? But if the defect is able to migrate, what it will happen is that is the temperature is such that these defects are able to diffuse. If they diffuse as they go along, when they come very close to the defect which is being present to a dislocation, okay, it will get attached to this region because the interaction energy becomes negative. Okay, then like that, so many defects will come, they will be drifting towards it. So the concentration of the defect itself, if we look at it, if it is Z0 is the initial concentration into exponential Kt. Okay, this way the concentration we will find that is going to increase. Okay, the defect will see. That means there will be atmosphere which will be formed around the defect core. This happens because the temperature is such that defect is able to diffuse. Okay, but at the same time, when the temperature is high and the dislocation is able to diffuse, there is another process which can happen is that as the thermal vibration also will increase with temperature. So that can make the atom vibrate and come out of that place. So if the temperature is very high, the thermal vibration also is going to play a role. It may so happen that at very high temperature, atoms come close to it, but they move away from it also because of the thermal vibration. Okay, that is generally this happens at temperatures less than 0.5 Tm, where okay, diffusivity is sufficient for impurities to migrate, but at the same time the thermal vibration is not sufficient for the atoms to come. So that means that there is a net concentration increase of the solute is going to take place around this location. If this sort of impurities atmosphere form, this is what is called as a Cottrell atmosphere. Okay, what will be the consequence of it? Now once an atmosphere has been formed, dislocation and the point defect is there where it's in a low energy configuration. Now we apply an external stress, okay, in this direction. Suppose an atmosphere has formed around this dislocation. If we apply an external stress to move it, it has to, the stress which is required for the dislocation to move in the absence of the atmosphere is some value, but when an atmosphere has formed, it requires higher stress to move. Okay, that means that suddenly you find that the yield stress is going up. This effect is in metallurgy parlor, it is called as static strain aging effect. Okay, what is static strain aging effect? is quite simple. If I am doing a mechanical testing of a sample, okay, an alloy, I do a test, okay, try to look at the stress strain plot, okay, it has reached at some particular point, I unload it and bring it there to room temperature. If I load it again immediately and bring it, then what I will observe is that at the same point again the yield stress will come, it will try to the stress response will be starting from here. Suppose I leave it for some time at that temperature, then that's I am giving sufficient time for the defects to diffuse to a lot of dislocations which are there. Then they form an atmosphere around it. Now the stress which will be required becomes rather high. Then the stress will go up like this, and at this, then once it breaks away from the dislocation from the Cottrell atmosphere, the stress will come down and it will come like this. This is what essentially we see in the case of iron in interstitial elements. Because what happens in the case of interstitial elements is that even at room temperature, the defects are sufficiently mobile, interstitial defects. Okay, so they can form an atmosphere around the dislocation. That is why in pure iron, if BCC iron, when we test it, we find that it always there is a yield phenomena which occurs. Goes up, then it goes like this, correct? This is because at this higher stress is required for the dislocation to be freed from the atmosphere. This phenomena is occurring because of this dislocation defect interaction. Okay, that's what I wanted to tell. This we call it as a static strain aging. Suppose this process itself occurs during the test, okay, then this phenomena we call it as dynamic strain aging. Okay, or DSA. There are many manifestations of DSA. The whole talk is not on that aspect of it, but what I wanted to understand is that out of the many manifestations, one which is normally prominently seen in many of the materials is what is called as a serrated yielding. Serrated yielding is a phenomena in which there are low drops like this, it goes. This is occurring because of one of the reason is that when the dislocations are moving in the material, a lot of forest dislocations are there. The dislocations get stopped at the forest dislocation. When the dislocation is stopped at the forest dislocation, the defects can come and form an atmosphere around it. The applied stress is also increasing. The internal stress also is increasing because an atmosphere is forming. At some particular point, if the applied stress becomes sufficiently high to overcome this atmosphere, then the dislocation will move out of it. Then there will be a drop which will be seen. Okay. Again, next obstacle it goes, there it will be stopped. Like this is what is going to happen. Okay. Then there is some negative strain rate sensitivity effect, and this phenomena is very important in mechanical behavior of material because this can alter the total elongation, okay, yield stress, ultimate tensile stress. There are lots of properties have been affected, especially when the material has to be formed at different temperatures. Okay, the amount of energy which has to be put to process the material to different shapes will depend upon what all the phenomena which occur. Dynamic strain aging is one important phenomena which has to be considered. Okay, this phenomena, the way I look at it is that many people report this phenomena, but the basic understanding of it especially the manifestations of this phenomena, is still, I feel that on the theoretical side, a lot of work has to be done to get a very clear picture of it. Okay. So what we have considered is the solute dislocation defect interaction, okay, either point defects or impurities, and what is the consequence of it, one of the effect, correct? Let us now consider the other effects. Another important effect of these point defects is if we take a material and irradiate it, okay, then when we irradiate it, either it's with self ions or different type of ions which are accelerated to high energy, or with neutrons in a reactor, okay, atoms are displaced from the lattice site. When these atoms are displaced from the lattice, lots of defects are introduced. These point defects and these vacancies, they can agglomerate to form different types of clusters, defect clusters, as well as some loops can be formed. Naturally, when we deform this sample, the dislocation has to overcome all these obstacles, and this also gives rise to hardening. This is called as an irradiation hardening. This has an effect on creep so many other properties of the material. Okay, there are some cases which has been observed that, like in stainless steel, sometimes this itself gives rise to what is called as dislocation channeling. There is a softening of the material is noticed when you do a subsequent mechanical testing. That is thought to be that these defects interact with the dislocation which has been generated. They annihilate and create a channel which is free of defects, within which the subsequent deformation could be propagated. Okay, this is one of the things. Okay, so far we have looked at it essentially a dislocation defect interaction. Okay, looking at only individual one. Now suppose, let us consider a case, these defects are distributed uniformly in the material, okay, or in materials which contain a second element, okay, as an allying element, at a temperature at which we are doing the heat treatment. Okay, the solute supersaturation is there, that can come out and form a second phase particle. Precipitation can occur. So these precipitates are nothing but a volume defects in the material. Okay. So far in this course, though initially I mentioned that volume defects are two types. The three types of volume defects I mentioned: stacking fault tetrahedra, okay, precipitation, and voids. Okay, voids can form during irradiation. Stacking fault tetrahedra can also form in some materials, okay, because of materials with low stacking fault energy, because of some specific type of dislocation interaction. Okay, precipitation can occur, okay, when supersaturation is there. That aspect I did not go into a detail, okay, just mentioned it, but essentially this part of phase transformation, that is why I had not gone into a detail. But what we will look at it is, that's also a defect, volume defect. What will be the interaction of dislocation with these defects? That's what we will discuss in this class. Okay, suppose these solutes are distributed uniformly in the lattice, okay, then the interaction with the dislocation can take place with two different ways. One is the interaction could be very local, unless the dislocation comes and goes close to the defect. That is, suppose a dislocation is there, some defects are distributed there like this, okay. Unless the dislocation is very close to the defect, there is no effect, okay. Then it's called as a local interaction. In some cases, the interaction itself could be a diffuse interaction, means that the long range interaction takes place between the solute atoms and the dislocation, okay. Both the types of interactions can take place. Like in the case of a matrix, whenever an interaction is going to take place, where the defects are distributed uniformly, then that interaction is going to be essentially a diffuse type of an interaction. With respect to a second phase particle, when an interaction is going to take place, it will be a short range interaction when the dislocation comes very close to it, correct? Okay. What is going to be the effect of this interaction? Let us assume that in one element, we have put on another element where that misfit is large. Okay, it could be a positive or a negative misfit. If we introduce that, okay, that misfit will, the atom which has been introduced, okay, one, it can appear as a strain because the lattice parameter change is going to take place, correct? That we can say it in another way, that this interaction energy which we consider, what we have looked at, dislocation, this one, that interaction energy itself is, if we take the rate of change of interaction energy, that will be giving a force, okay. Some stress is being generated, internal stress is being generated. Initially, the dislocation is able to move at a lower stress. Now we find that a higher stress is there. That is some internal stress which is opposing it is created because of introduction of these impurities into the material. Okay. Suppose this interaction itself is a very diffuse one, okay, in the sense that the defects are present at various regions. How do we consider interaction as defect is diffuse? That is, suppose defects are present like this. Suppose the dislocation moves like this. This means essentially it is a locally there is a variation which is going to be there. Other way in which it can happen is that the dislocations are present. That is, here it is not interacting particularly with any this one, but the effect of that defect has a long range interaction which is going to be there, correct? That is, interaction is essentially a long range elastic interaction which is taking place, okay. When such long range elastic interaction takes place, one of the things is that overall there will be a bending of this dislocation, correct? When a bending of a dislocation takes place, okay, then what is the radius to which they are bent, okay? That is, 2I is the, B is the Burgess vector, this is the force, this should be equal to some T, okay, the line tension of the dislocation. From this we can find out that I will be equal to half GB squared, okay. So this will GB by 2R, from which we can find out what will be the R, correct? So essentially this tells us, this is with respect to a particular defect or some concentration of defects which are being present. So this, if we average it out, some statistical value which will give, that gives the total, this one tau to be equal to, I think 2 by half tau I. This will be an average value, because in all these calculations when lot of particles are involved, we have to take an average of it, okay. Is it clear? No, I think here it is 2 by pi only, okay. This also we can calculate what is it going to be. Another, okay, this tells out about what will be there. Then some more factors which we have to consider it is, okay, this interaction, suppose different particles are present at different places, okay. There is an interparticle spacing which is going to be there. How do we take out the interparticle spacing? One is we can assume this is a random distributed particle, then the average interparticle spacing will be square root of if the number of particles per unit volume is n, okay, unit area is n, then 1 by root n, that is will give that a value, okay. That's the way we can do it. Let us now look at the interaction which is going to be a strong interaction. Okay, that means that unless the dislocation reaches very close to the particle, there is no interaction takes place. Let us take a case start here like this. Okay, there is a dislocation line which is there, and as this dislocation line under the action of a stress moves and reaches here, comes here, under the action of the applied stress, these obstacles will put a resistive force. Because of the resistive force, the dislocation will bend like this. Okay. This is how it is going to take place. So essentially, the interaction is only at this point. So essentially, if you look at it here, there is going to be a T is the line tension. With respect to this angle we can calculate. This is going to be the resistive force which it is going to, okay. What will be this resistive force K? That will be equal to 2T if this angle is phi cos phi, correct? That's what the resistive force which is essentially going to be. And suppose this separation is L from here to here. It bends into a radius, correct? Is it not? When it bends into a radius, what will be the force which will be applied force which is going to act? That's going to be tau into B, okay, into L, the separation between them. This is going to be equal to the force K, okay. And this is a very critical one, okay, and K can be written as 2T cos phi, okay. What is the critical stress which is required for this to be able? That is tau max. What is the stress or critical stress which will be equal to? This will be K by BL, K max, okay. This will be 2T into cos phi, a critical value will be there, maximum value, divided by BL we can put it, okay. This is essentially what is the stress which is required, okay. Suppose now the most critical crucial point of it is that at some value of the line tension corresponding to some particular angle, the K max reaches where the dislocation is able to shear through the particle. Because the dislocation has got a the line tension depends upon half GB squared, the modulus of the material. It has nothing to do with that particle, okay. It's able to reach that value, then it will just cut through the particle, right? And suppose it's not able to cut through the particle, there is another critical value at which it can loop around this particle. That will decide whether it's going to be shearing or looping, which is the mechanism which is going to operate in this interaction, dislocation precipitate interaction, okay. And another factor also which has to take it that here we have taken L to be these particles are like this, but normally what happens is that whenever a deformation takes place, quite often in these regions, as you can see it, the dislocations may be like this it may be going. That means that the dislocation line, if it is a straight line, then we can calculate and tell that the line spacing is equal to 1 by root 10. Okay, but that will not be possible when the dislocation line is not a straight line. That means that some statistical averaging has to be done. Okay, that statistical averaging which has been done, that is called as a Friedel spacing. Okay, that Friedel spacing, essentially the formula is this is the spacing which it is going to have is L minimum, which is given by when it's a dislocation, it's a straight line, the minimum spacing into 2t by f0. What is f0? f0 is the different type of interaction which it can have, the dislocation can have with the particle. Okay, like it could be an order hardening. There are so many types of mechanisms which can happen. That will have some maximum value which is required. Okay, that is what essentially this F0 represents, the force corresponding to that. Okay. In this case, we can consider two cases. Suppose this this phi becomes 90 degree, then K max will be equal to 2t. Then the dislocation is essentially a straight line which just cuts and goes with whatever is the stress which is being applied. Let us take an intermediate case where it's a critical angle is there. When it is bent like this, okay, it has reached a value where it is able to cut and go through it, correct? And when this value of phi becomes 0, consider that case. At that point, it's not able to cut. Then what is the consequence which will happen? At that particular point, when phi equals, I'll just essentially the dislocation is bent like this, correct? The tangent, essentially angle becomes 0. Okay, this has become a semicircle. Okay, when it has become a semicircle, from the Peach-Coiler force equation, we have understood that the force is always going to act in this line direction, perpendicular to it. So here the force will be in this direction. Here the force will be in this direction. This will make the dislocation move like this. Here it will move like this. This will move like this. Finally, both of them will come and join together. Okay, and this dislocation will just come out of it as a straight line. So that is the critical condition when phi equals 0, where the looping will take place. That is over one looping. Okay, so when phi equals 90 degree, we will call this as a weak obstacle. Okay, the strength of the particle changes in between. Is this clear? Okay. Now, here we mentioned that this phi is determined by the strength. What is the strength which we will consider it? There are many parameters which can be considered. One, suppose these are two different phases, both are disordered, and assume that both have got the same crystal structure. Then what will happen is that, and for the moment we consider that the lattice parameter remains the same. Suppose the modulus is different between these two, then what will happen? The modulus will determine what is the stress which is required. Suppose this has a modulus which is higher. So to account for the modulus, if it bends a little bit, the line tension becomes sufficient. It can make the particle cut through it. So modulus also plays a role to decide, correct? Another is that suppose there is a lattice parameter misfit is there. Okay, we have seen that interaction which can happen. Okay, lattice parameter misfit. Not only that, in that particular case which you have considered, there is going to be a strain which is accommodated around it. This strain we call it as a coherency strain, which we have talked about in the last class. Okay. So with the coherency strain, the dislocation can interact, and depending upon the sign of the strain, positive or negative, it can be an attractive or a repulsive interaction. Okay. That also puts an effect on what is the stress which is necessary, critical stress which is necessary for the dislocation to overcome the particle. Stacking fault energy in the matrix and in the precipitate could be different. Then if the variation in stacking fault energy is there, that much energy difference also may be necessary. The force necessary to generate that much of stacking fault energy also has to be provided for the dislocation to pass through it. Correct? That's one which will occur. Then other is order hardening. Suppose this particle itself is, suppose these are all, we consider it as a large particles and they are ordered. Okay. Then the dislocation as it comes and touches here, for the, even if the crystal structure remains the same, lattice parameter remains the same, as the dislocation moves, first dislocation, it moves atom from the right position to the wrong position. Okay, that means that antiphase boundary is created. That much energy is also necessary for the dislocation. So in that case, the force which we consider F will be equal to gamma into D. This is what it will turn out to be, where gamma is the stacking fault energy. Okay, these are all the various types of. Then one more. If the dislocation passes through the sample, that's you assume that a dislocation is there. This is the precipitate. The dislocation, this is the slip plane. As the dislocation has come out of it, what will happen is that it has created a surface on the surface to the, so extra energy is required to create this surface, that energy. So surface energy can be different for different type of particles. So these are all the various types of mechanisms. So essentially what we have looked at, it is modulus, okay, lattice mismatch, and which is called as coherency strain. Okay, then surface energy, because extra surface is created, stacking fault energy, then comes antiphase boundary, or this is called as sometimes order hardening. Okay, that when the dislocation it has to disorders the ordered lattice. So all these effects are going to contribute to strength. Okay, as I mentioned earlier, depending upon where it is, okay, where the dislocation is, as the dislocation enters, different type of interactions will start. Okay, so if it's a coherency strain around this particle, there is going to be a strain around it. Okay, so as the dislocation reaches here itself, the coherency strain part will be acting. Order hardening part will act only when the dislocation tries to enter into the particle. Okay, that will be changed. So all these effects are going to act at different instants of time, at different positions with respect to the particle. Okay, the sum of the effect at each point, it will be changing now. That will reach a maximum value at some particular point. That maximum value is the stress which is required, okay, for the dislocation to overcome the particle. If that stress turns out to be much higher, okay, than what the line tension can provide by bending it, then what will happen is that the looping will take place in that case, right? This is what essentially which happens. Is it clear? Okay. Depending upon this, the average distance between the particles, some expressions could be derived for the modulus each of this hardening effect. One can calculate what is going to be the critical stress which is required. Okay. Generally, the various stresses acting together, there are many ways in which this is being taken. One, if they are all, this could be sigma into I can write it because of various effects. That's one way. There's another way in which it is done is that I squared. Because this, depending upon the type nature of the forces, in some cases where the stresses are vastly different, then it's a simple addition which is taken. When they are all of the same magnitude, essentially they are squared, added, and the square root of the mean is taken. Okay, this is a standard procedure which is followed in other branches of science also. This essentially tells about the hardening. Now let us just consider one particular case which I just wanted to tell, is that whenever these precipitates are or these particles are not disordered, because we consider two cases. These particles have a finite radius but they are disordered, and another is order hardening comes in the case where the particles have particles are ordered. Okay, suppose ordered particles are there. Okay, then what happens when the first dislocation passes through the particle? It disorders it. Okay, depending upon the crystal structure difference between the matrix and the precipitate, or the crystal structure of the matrix and the precipitate, groups of dislocations have to pass through. In the case of gamma prime precipitation in many of the nickel based superalloys, okay, essentially the crystal structure of the ordered phase, the gamma prime, is L12, and the matrix essentially is gamma. Here two dislocations, that is in the FCC matrix, essentially A by 2 110 is the Burgess vector of the perfect dislocation. Okay, Burgess vector of perfect dislocation in L12 is essentially A110. Okay, but what is essentially is going to happen is that this, since the magnitude of the Burgess vector is large, the self energy is high, so because of that it would try to split into superpartial. All these aspects we have considered earlier. Okay, if a superpartial is passing, that's nothing but a Burgess vector of okay. The first dislocation, what it happens is that it will come this is the way it will be happening, because it has just entered. Here also it has entered. Here it's about to enter. When the second dislocation comes, this is an okay. The first dislocation generates APBs and the phase moment. The next dislocation which follows, suppose we say this is D1. Okay, the next dislocation which it comes, it is nearly straight because it's seeing only a ordered lattice. It's seeing it's seeing a disordered lattice. In a disordered lattice, if it doesn't see any obstacle, it will be a straight dislocation. Okay. And as this dislocation comes very close to it, since the Burgess vectors are the same and they are lying in the same slip plane, they will repel each other. Okay. Correct. And as it passes, restores order. That's a gain in energy is also going to be there corresponding to the order energy. Correct. This will lead to a sort of a situation, okay, where we can write a force balance equation for these two dislocations. What are these two equations? This equation is for the first dislocation, the applied stress, the force which is acting on this. This dislocation puts a repulsive force onto it, that also adds to it together. These two should be managed by equal to the order, the antiphase boundary energy which has to be generated. When they are in equilibrium, this should be equal to 0, correct? For the second dislocation, what it happens is that this is the applied stress, okay, this is the interparticle spacing. Then this will put a force which is negative of it onto this one, plus some gain in this is going to be there. If we solve these two equations, okay, then we will be able to get okay, this is the sort of an expression will come. This is gamma is the antiphase boundary energy. This is the Bajs vector of the dislocation. This is d1 by L1 is the d1 is the average distance which the dislocation has cut in the particle, this dislocation 1, and L1 is the average spacing. Similarly, L2 remains that, and D2 has that same meaning. Okay, these one can, there are some formulas with which one can find out. Okay, this gives the expression to find out what is the critical stress which is necessary. This will be the increase in yield strength which it will occur when we deform a material. In all these things here, you can see that the dislocation has been already bent into a this one. Suppose even before the dislocation has entered, it has already reached a semicircular one. Okay, then what will happen is that it will not be able to enter into the particle. Instead, a looping will take place. That will occur when the particle spacing is large. For the same size of the particle, if the spacing is large, then it can occur. Okay, if the spacing is small, that means that the volume fraction remains the same and the number density is getting reduced. Then what is the consequence of this as the volume fraction and the number density changes is that when we do a work hardening plot, okay, the YS versus particle size, if we plot it, or versus the distance if we try to plot it, we will see that it goes to a maximum and comes, correct? There is a maximum hardening region is reached and then it starts decreasing. Okay, I don't want to go into any of these aspects of it because I am confining myself here only to a defect interaction. This is the sort of an interaction and the stresses which it will introduce. Okay, so from this region, it's essentially going to be a looping which is going to be the predominant mechanism. Suppose it's not a second phase particle which is produced, it's a dispersion hardening. We have put an oxide particle into it. Nowhere the dislocation can enter and cut the particles. In such cases, only a looping will take place, will be the main mechanism of deformation. More information about how this affects the mechanical properties, especially the yield strength and all flow stress, that on mechanical behavior most of you will be studying. Okay, that is not the objective of this course. Okay, now we will stop here. Okay, so essentially what I had given is an overall view of the point defect dislocation interaction, and point defect, the dislocation volume defect interaction. Dislocation interaction has already been covered earlier. So almost all the types of interactions which are required in a single crystal which we have covered. The other aspect of it is that the dislocations can interact with the grain boundaries. That part of it is level. I don't want to bring it at this particular level. Okay, that's also one thing which has to be done, because that also gives rise to hardening. That's what the Hall-Petch relationship which corresponds to. Okay.